View of other proof systems. First of all, proof systems that are based on linear inequalities, but not only. So let me just repeat the things that all of you know. So cutting planes has a linear combination rule and the rounding rule. And ResCP, or resolution over cutting planes, operates with disjunctions of inequalities. And also, in addition to the two previous rules, there is also the rule of integer negation. And then the rounding rule is actually not needed because it is simulated by integer negation. We will be considering a weaker system where we replace the integer negation by just the axiom, the corresponding axiom about a single variable. Okay, so it's somewhat forgotten weakening of areas of CP 20 years ago. Okay, so what do we know about these old systems? We know exponential lower bound for cutting planes by Pavel. And we know quasi-polynomial simulation by Noah and other people of tree-like res CP with small coefficients, which is called also stable planes with small coefficients, and it gives an exponential lower bound for this tree-like system with small coefficients. And also with small coefficients, res of CP is equivalent to its system that does not have integer negation. And when I was preparing this talk in Oberwolfach, Mark let me know that there is a new result about quasi-polynomial monotone interpolations for tree-like res CP with arbitrary coefficients. So it's also a lower bound, but still for tree-like system. So this question is left. There is an extra star. No, not an extra star. It's in place. Okay, so. But still, we don't know for extension lower bounds for daglike and even for small coefficients. Now, let's speak about tropical arithmetic. As I said, we have two operations, minimum and integer addition. And the minimum takes place of addition. It's tropical addition. And integer addition takes place of tropical multiplication. What are the neutral elements? It is 0 for integer 0 for multiplication, and for the addition, for tropical addition, what is the neutral element? It is infinity. We can work with that as with in this plus we can also write monomials, polynomials. Just we have a different notion of multiplication, so of powering as well here. And the neutral element makes an empty monomial, the only monomial that always has coefficient infinity. Any other coefficient is nonsense for this monomial because no sense to add anything to the infinity. And the tropical polynomial is, of course, a sum of the tropical monomials. Oh, tropical, not monomials, tropical terms, where term is a monomial multiplied by a constant. An inequality is an inequality. And let us now convert this to the usual terms. What is an inequality between two tropical polynomials? It is a conjunction or of disjunctions of linear inequalities. So we write the minimum of linear functions as at most minimum of other linear functions, or we write such disjunctions for every L which is on the right hand side. That is semantically equivalent. If any question, just ask. Okay, so now how do we prove things here? As we have polynomials, we have a kind of Nullstellensatz. It was investigated in several papers, including the paper by Grigoriev and Volodya Podolsky, who had in particular completeness result in several versions. And it justifies somehow what we are doing. So what is a Nullstellensatz proof system? We multiply the initial, so initially we have inequalities. We multiply them by polynomials, and we take a tropical sum. We do it on both sides of the inequality, and we treat this as a contradiction if for every monomial on the left-hand side the coefficient is greater than the coefficient on the right-hand side. Let me give an example like this. Okay, so you can read it in, tropically or in the usual terms. So every tropical monomial, this is a linear sum, has plus something on the left with respect to its appearance on the right. And then it's of course a contradiction. It's the notion of Nullstellensatz proofs. Yes.
You probably said this, but just not to get lost in the tropics. So sure, variables are still 0, 1. Like tropical 0, tropical 1.
Question. For now, I did not say what are the variables because you may want to do something not for Boolean logic, but think about them as zeros and ones. Yes, if you are in Boolean logic, think about them as zeros and ones. No, it's another natural setting is when there are 0 and infinity. But we will be mostly using zeros and ones. Now, what is a polynomial calculus? It's like polynomial calculus. It's you are making your Nullstellensatz refutation step by step. You take the tropical sum, you multiply. It's better to multiply by a term rather than by a polynomial, just to keep the complexity clear. But you understand that they are equivalent, of course. And also, important thing. Also, we use the transitivity of the inequality relation, and it indeed changes the things. And an important thing is that we have inequalities of tropical polynomials. So when we write this and want to conclude that f is at most h, we actually have here many statements inside, because here g is a minimum and here g is a minimum, so we cut many things, not just one.
That's it. Make it just it looks like the inequality in green is
Can you please say it loudly? I do not hear you.
Sure. To me, it looks like the inequality in green is backwards. Is there a reason for that?
Maybe
It's a
can
proof of
anyone-
unsatisfiability.
Can anyone repeat?
Oh, but we're proving that it's unsatisfiable.
The green inequality is a contradiction, right?
Yeah.
The green inequality is an example of a contradiction, yes. Okay, so in addition to these fully tropical things, so to say, or fully mean plus things, we will be using a tropical resolution rule, which is an analog of resolution rule in ResCP, where the resolution is made by taking a sum of inequalities. So the tropical resolution rule, if you read it in the usual terms, it will be the same. And it's somewhat easier than other things because we have 0 on the right hand side, so it's even easier to translate into the usual terms. So essentially that's it. But we do not need tropical resolution rule for completeness at all, and this is important. Tropical resolution rule is only a bridge between tropical systems and ResCP and so on. Now, just to give you several examples. So examples will be later. General picture, we will come back to it. But the general picture is that we have two hierarchies of systems that are parallel to each other. Those with linear recipients and the like. And for tropical systems where we have static systems like Nullstellensatz, tree-like, daglike systems, and the relations between them, something is known, something is very much work in progress. Okay. So let me show you an example. The first example is the pigeon-hole. How do we prove the pigeon-hole principle tropically? I will start with a conventional proof in ResLP, in tree-like ResLP. It is reminiscent of tree-like CP proof. I am not sure to whom it contributes. The difference is that we don't have rounding rule now, so we will avoid rounding. So what is the main thing in proving the pigeon-hole principle? It's to derive long clauses from short clauses.
Shouldn't it be less than 1? The SN less than 1?
SN, it's almost 1.
In the statement.
In
the statement of the lemma, why is it SN less or equal than 1?
That's we want to derive from
yes,
from these short ones, these long ones. That is the sum of many variables is still at most 1.
Okay. Yes.
Not
Yeah,
those long
yes,
inequalities,
yes.
but those long.
Yes. Okay.
Okay, and so how do we do that? So by induction, add the xn to both parts. We are adding another. Well, okay, what is it? Another pigeon or whatever. We add another variable to both parts of inequality. Then we add the many short inequalities to our induction base. And this way we get something like that. And using the disjunction that is obvious in the case of ResLP, xn is at most 0 or not xn is at most 0. Sorry for using dual variables. There will be a reason for that later. But for ResLP, it definitely doesn't matter, yes, dual variables or not. Using that, we get what we want. And one important thing here is that we didn't really use the full strength of resolution in the SCP. Namely, we only used when we took a sum, we did it for a very short disjunction. One disjunction is of size 1, another disjunction is of size 2. Do you have a question? So we can switch to tropical proofs because of that, because we don't need this resolution rule. And this is how it looks like in tropics. And so at the last step of this, we take a tropical sum. I wrote substitute. Actually, we are using the transitivity of the inequality relation. And here you see that there are two terms, and we are using the transitivity immediately for both terms. Some technicalities are needed here, but it is close to the full proof. Now another example is how we simulate daglike resolution in static tropical proof systems. A clause is translated as it is translated in pattern plane, so it's the sum of literals, and it should be greater than 1. And now we observe the following thing: when we have a resolution rule, then actually, even if A is not derived by resolution, just any clause, then we can not just prove, it is almost trivial, but it's easy to prove that the corresponding tropical inequality that says that actually that formulates the resolution rule for A, it is derived and easily derivable in tropics. And now we stack all these resolution steps into a single static proof by providing them with some additive coefficients. Why additive coefficients? Important thing. If you have such a rule and you want to make it static, what could you do? You take the minimum, the tropical sum, but what would you get then? You would get that the minimum of f and g is at most the minimum of g and h. But this may be trivial. Even it's not very interesting. We want to get rid of that g, and in order to get rid of that g, we add something or multiply tropically or add. Let me write in the okay. So we add some epsilon here. Of course, it's valid thing, and then we get rid of g because it has a sorry. In here there is a subtract some epsilon, or did I did it right? No, epsilon. Okay, just it's here. So we this way we get rid of g because we have greater coefficients for g here or there. So forget about g after that, more or less. But it is at the expense of plus epsilon here. So we, instead of f is equals to h, we have something a little bit more or less. F is at most h plus epsilon. But if epsilon is small enough, then it's we take the tropical sum statically of all resolution steps, and that's a static proof. Now to the question of Jakob, how do we encode the zeros and true and false? The most obvious way is to say that x plus the negation is 1x and the minimum of x and the negation is 0, and translate Boolean clauses in the same way like in cutting planes. There is a different way of doing that, namely we can formulate it this way, or in the usual terms, it means that the minimum of 2x and 1 is x. And the same thing in ResCP, but not the same thing in tropics. It makes without the dual variable, the things become much harder. Now one could also consider zero infinity encoding for true and false, and this way we get res infinity. Let me call it res infinity. Maybe it's like depth too freaky, but for sure that can call infinity. Exactly. That's the polynomial calculus, tropical polynomial calculus is exactly res infinity. Now what can we prove with respect to lower bounds? Not much so far, but a little bit more. A lower bound on the tropical degree for the refutations of this Krajicek problem with the encoding with that encoding without dual variables. Then the size bound for a stupid equation, for a stupid binomial, which is like the binary value principle cut its largest term. The size for such tropical degree must be the same as almost the same as the degree itself, and if the degree is exponential, then we need the exponential many steps. Now there are many definitional issues about whether we can use just integer coefficients or we really need rationals. Remember about this epsilon. And in static systems, we do need rationals. In dynamic systems, it is more complicated. Sometimes we do need them, sometimes we don't. And one important thing is that the tropical resolution rule is not derivable, and since, well, it's proved that it's not derivable statically, but we are not concerned here about the complexity, and so it's not derivable even dynamically. And that means that a direct simulation of, let me come back to the picture. It means that a direct simulation of the polynomial, tropical polynomial calculus with the equivalence with the res LP is not so trivial. There is an equivalence between res LP and nucleus polynomial calculus if we add this resolution rule. Without that, there is no equivalence. That is, we can't prove it. And probably there is indeed no equivalence by this. And even such simple things like the non-negativity of a variable are not derivable if you take that alternative axioms for zeros and ones. Now I have two slides about open programs and again a picture for that. But let me start with the picture just to remind what we have here. We have ResCP, and then we have a hierarchy of tropical systems and also more known and investigated hierarchy of recipe-like systems. So what I said is that without the tropical resolution rule, it's not clear whether we can make here the equivalence. Red means that I don't believe it. On the other hand, we can simulate a resolution in static systems, and the question is whether we can simulate cutting planes. I tried, did not get it, almost got it, but not quite. So I believe that cutting planes should be simulatable, at least in the polynomial calculus here, but other things are less clear. So in general, a word of caution, when we are talking about tree-likeness, we need some other word for tree-likeness. Tree-likeness is different in the usual setting and in tropical systems because innocent multiplication by a bit constant in cutting planes. For tropics, it's something that needs deg. And the other way around, the transitivity of mean plus polynomials, it is a simple operation in tropics, but due to the contents of G, it is daglike in the usual setting. So what is, apart of what I said, what is most promising here with respect to lower bounds? It is that stupid encoding. It is that stupid encoding that the minimum of 2x and 1 equals x. It's difficult to prove anything in this encoding, so it's but it's absolutely unclear. It's where the further research starts. But there are chances, given the impossibility statements that we have, there are chances that there might be some lower bounds for this. And the last but not least, nice thing about mean plus proofs, especially static proofs, is that lower bounds for them can be obtained just by analyzing the coefficients because it's static, but just by analyzing the coefficients between left and right for different monomials. Thank you.
I'm not very about how kind of operations we should take them offline. So the title group meets